Okay, hi. This is a citizen speaks, and I would appreciate it if you click the like button or subscribe. It encourages me to continue recording these videos. Um, so let's try the new one. This one's a little bit more complicated, but hopefully interesting to all of you. It's called God and Infinity. Reading Cantor's Elements, Grundlagen in German, I'm reminded of the intricacies of rigorous mathematical exposition, so hard to understand for most of us. I find facts about his life that are pertinent to achieve some understanding about Cantor. He was a Christian, believing, as so many of his predecessors had, that his goal was understanding God's design of the universe, and in it the tiny ball of mud on which man has struggled to do that for tens, if not hundreds of thousands of years. He was not understood. Leopold Kronecker, his professor at the University of Berlin, who prevented him from joining the faculty there, considered Cantor to be a charlatan and a corrupter of youth. Other contemporary mathematicians treated his ideas with skepticism at best. Gustav Mittag-Leffler, a Swedish colleague and friend, wrote Cantor that a paper he had submitted to Mittag-Leffler's Acta Mathematica journal would not be understood for another 100 years. The many rejections and hostility of leading mathematicians like Kronecker took their toll on Cantor's life and career. In later years, he suffered bouts of depression, unable to convince so many of his contemporaries to accept his ideas about transfinite numbers and the importance of set theory in differentiating the magnitudes of countable versus uncountable numbers. Here we must discuss the meaning of the words countable and uncountable. As pointed out in the previous video on primes, divisibility, and infinities, the irrational numbers are uncountable since at best they are approximations between rational numbers. That makes them different since our representations like pi or square root of a prime number indicate numbers different from the rationals. The later can be connected to concrete problems, meaning the rationals, such as 2 apples out of 5 or 6 slices of a pie out of 8. The best we can do with irrationals is to identify them as approximate ratios of measures, like the circumference of a circle to its diameter. Because of the limitations of our abilities to draw or build perfect circles, and thus our inability to obtain exact measurements of their circumferences and diagonals, we find that there's no unique ratio that satisfies that requirement. Sorry. At best, we can identify values that are slightly bigger and slightly smaller than a number, and thus must conclude that there is no exact ratio for it, meaning the circumference, to the diameter. The problem with obtaining this exact ratio is connected to the fact that circles are obtained by increasing the number of sides of regular polygons, that is, ones for which all the sides are the same length. As the number of sides approaches a large enough magnitude, or in mathematical terms, infinity, we obtain a circle. This geometric process is one of the first that involves approaching that elusive phenomena we identify with the word which means endless, forever increasing in number. Philosophers and mathematicians not distinguished by the ancients had other encounters with infinity. Zeno's paradox involved the possibility of reaching a point if you are only to cover half the distance to it at a time. It involved the idea that a point has no dimension, which is only true as an idea, since in reality, even the smallest point has 3 dimensions. The first encounters with these numbers which played a role in building the infinite enthralled mathematicians. Since the ancients believed in powers exceeding their understanding and associated these with gods, or eventually with God, they believed that these irrational numbers were, in some unknowable combination, symbols and language incomprehensible to men. In the 16th and 17th centuries, men like Blaise Pascal and Isaac Newton, less modest because of predecessors like Copernicus, Galileo, Tycho Brahe, and Kepler, began to plumb the mysteries of infinity. For Pascal, the investigation led to that elusive mathematical concept called probability, the foundation of statistics so much misunderstood and misused centuries after him. Newton approached the problem of infinity by investigating the momentary meaning of the speed of an object. Since the classical way of measuring speed was to find the average distance covered in a given time, he sought to find a way to measure it at a given moment. This involved using smaller and smaller intervals of time, and as he found, could provide the measure he sought by finding the slope, or the change in distance over the change in time, or in other symbols, ds over dt, which is a derivative. And he thus arrived at the formula for the derivative and generalized it to apply to any continuous function, meaning a function that has no gaps in it. In the more complex polynomial functions, the ds over dt is a higher degree, thus more abstract function, and relates only by analogy to the simpler case of the slope mentioned above. By the end of the 19th century, with advances in physics, chemistry, and biology, the idea of the infinite was accepted as an important subject for study. Cantor's approach to understanding and analyzing infinity and the role that numbers play in it then does not seem untimely in retrospect. He preceded developments in physics like Einstein's theory of relativity and Niels Bohr's quantum mechanics by about 3 decades, not much of a lead time when compared to mathematical ideas like group theory, which, though initiated at the middle of the 19th century, did not begin to find applications in physics for almost a century. Cantor was ahead of his time as far as his mathematical compatriots were concerned. Let us look at a few unusual characteristics of numbers associated with infinity. If we consider a number of natural or counting numbers, we arrive at an infinite number. The number of counting numbers is infinite. Cantor assigned this number, the number of counting numbers, the Greek letter aleph with a subscript of 0. This is a countably infinite number, and interestingly, it is the same as the one for all even numbers, or all odd numbers, or all multiples of 4, or all multiples of 5, and so on and so on. Okay. What is more, it also applies to the number of integers, that is, the positive and negative natural numbers and 0. To see how this works, list the integers as 0, minus 1 plus 1, minus 2 plus 2, minus 3 plus 3, minus 4 plus 4, and so on. Going on forever. Crucially, these sets of infinite numbers are said to be well ordered, meaning that each number in a set is smaller than one number and larger than another number in the same set. No number may occur out of sequence with the others. We can show that adding aleph sub 0 to itself is equal to aleph sub 0. But since multiplication is just repeated addition, multiplying aleph sub 0 by any rational number will also result in aleph sub 0. To see what happens when you multiply aleph sub 0 by itself, look at a simple subset like 10 times 10. You can set up a 10 by 10 array to show that there are 100 numbers in the table of products. Doing this for an array which is aleph sub 0 by aleph sub 0, we arrive at an array of aleph sub 0 numbers. So even for this amazingly large set, the count is the same. The problem is different when we are talking about uncountable numbers. Some questions arise depending on how you use notation. Using pi, or the square root symbol with the prime numbers, would indicate that these irrationals can be counted. What is more, taking irrational numbers with numbers individually For example, the square root of 2, which starts as 1.41421356 and 3 dots, meaning it goes on forever. You can look it up on a calculator and see the number. Without repeating and knowing that we may create an infinite set of irrationals just by changing each digit. That is a set having 10 to the n elements, meaning each digit, there are 10 possible digits for each place, and I can have n of them. N is a number infinitely large, so it's 10 times 10 times 10 times 10 times 10 n times. The interesting thing is that since there are 10 digits in each place of this one irrational number, we could count the set of irrationals described in this process. Thus, for each irrational number, there's a set countable number of irrationals gained by changing its digits. We can do this for the square roots of all the prime numbers. Similarly, similar procedures may be used for Euler's natural base E and for other irrational numbers. The problem arises when we do not proceed in such an orderly fashion. Notice that we can arbitrarily replace any number of digits in the square root of 2 by any number of the same digit. For example, I could take 15 ones instead of the first one and then continue with 0.4142 and so on. Okay? Or I could take 15 twos or 15 fives or 15 nines and so on. Okay? And I could do that in any one of those places. And I could do it 15 or 12 or 5 or 6 or whatever number. Okay? So we have no way of knowing how many digits are to be replaced at any time. The ordering of the new set of irrationals this way, with all those repeated digits, is not easy as in the first method we used. This is especially true if we randomly introduce repetitions like the one above anywhere in the infinitely long irrational number. The uncountability becomes a bit clearer if we look at each irrational number as the center of a decreasing interval between two rational numbers, which was the way Cantor looked at them. In the case of the square root of 2, we start with the open, not including endpoints, interval from 1.41421356 to 1.41421356. So the last digit in the first one with 8 decimal numbers before the 2 is a 2, and the second one, the last digit with 8 decimal numbers before it, is a 3. So that the interval is very small, but there's a little bit of interval between the two. As we proceed to make the interval smaller and smaller by adding appropriate integers to the unincluded endpoints, we approach but never reach the irrational square root of 2. This approach involves limits. That is, the limit of this increasingly smaller interval is the square root of 2. The question is, can we count that point or number, since it is so elusive? Cantor argued that it, just as the other irrational numbers, was uncountable, because he proved that in any interval like the ones mentioned above, there will always be an infinite number of uncounted real numbers, meaning irrational numbers. That also leads to their property of not being well ordered, unlike the rationals. There are mathematicians who disagree, using the properties of limits. Their arguments are worth pursuing, but they're pretty interesting, but not easy to follow. The question is, if we use Cantor's symbol for the irrational numbers, aleph, is their uncountable infinity equal to or greater than that of aleph sub 0 infinity, the magnitude of the set of rational numbers? According to Cantor, aleph, because of its uncountability and lack of order, the magnitude of its infinity is greater than that of aleph sub 0. That statement leads to interesting results. What happens when you add the two kinds of alephs? The new set will have the magnitude of the larger one. Similarly, for multiplication of the larger set by the absolute value of any integer, and for the multiplication of two different magnitude sets, you'll still get aleph as the number. Having reached that point, Cantor developed a new algebra for these infinite or transcendental numbers. That's what he called them, transcendental, and the sets that contained them. He was beginning to analyze the language in which God wrote the universe. As for most mortals, even for ones as brilliant as Cantor, approaching such mysteries is fraught with danger. Mathematicians, the only ones who could understand his ideas, were at best skeptical. Even when they understood them, they could prove them only using accepted mathematical concepts known as a priori. A priori is simply something that is assumed true from the start. It's a Latin expression that means relating to or derived from by reasoning from self-evident propositions. For example, it is possible to have infinities of different magnitudes. That's an a priori assumption. Cantor posited his proposition based on the distinction between countability and a lack of it. Again, an assumption that is not a priori as evident as the one that two objects are more than one. In the past century, there have been many who have understood and agreed with Cantor's theories about transcendentals, and some who have countered with objections and counterproofs. The later tend to argue with Cantor's idea that irrationals are not ordered, and that is what makes them uncountable. Some argue that the intervals of rational numbers which converge to irrational ones based on the nature of limits imply that there are points associated with irrational numbers. They refer to the density theorem in algebra that says that each point on the number line has a real number associated with it, and for each real number there's a point on the number line. That means there are no gaps or discontinuities in the number line. That algebraic geometry argument is weakened when we consider Cantor's proof that between any two rational numbers, there are infinitely many irrational numbers. There are also infinitely many rational numbers between any two rationals, since we can always divide the distance between them into decreasingly smaller fractions, for example, 1/2, 1/3, 1/4, 1/5, and so on. But Cantor argued that irrational numbers could not be counted, because as mentioned above, they cannot be generated systematically. We arrive at a conundrum. One, like many that have recently baffled us in physics, chemistry, and biology. Quantum mechanics, subatomic particle physics, mass-energy relationship, dark matter and dark energy, and the mysterious complexity of cellular functions are just a few examples. What they teach us with each new discovery is that the more we know, the more limits of our knowledge are expanded. They may be larger, but they are there. It is as clear now as it was for Socrates, who claimed to be the smartest man in Greece since he was the only one who knew his own ignorance, his inability to know beyond certain limits, which even if they expand, reveal newer limits. Let us leave the conclusion to the listener. No matter how well we plumb the mysteries which confront us, we never achieve complete understanding. The limits keep expanding. Men like Cantor understood where such reasoning led. Just as beginning is unknowable, so is the end. Let us close with Pascal's pensée, that is thought, number 792. The infinite distance between body and mind is a symbol of the infinitely more infinite distance between mind and charity. For charity is supernatural. Well, that's it. Another video for Citizen Speaks. I hope you liked what you heard. And if you liked it, did you click the like button? And even more so if you've subscribed so you can see the next ones. I appreciate your attention, and I hope you come back again. Wish you all the best. Take care.